So I do want to touch a little bit on voltage divider rule as well. Alright, so voltage divider rule, when do we use this law? Alright, we can use this when we have anything to do in a series circuit. Alright, let's say you have a combination of few resistors, okay, for example, and then you know that the voltage source here, denoted by E, your voltage source is 10. Alright, I have two resistors. Okay, so if I want to know that let's say like the voltage that goes across this 8 kilo ohm thing over here, alright, V2. So how do I find V2? V2 is basically it goes by this formula. You take the resistor of which the voltage you want to find. This is R2, right? So you take R2 over, and then you take the combination of all the R's that you have in a circuit. In this case, you only have two R's. So basically, it's R1 plus R2. Let's say if I have more resistors, then you just plus all the way up at the denominator side here, the downside here, yeah? And then you multiply with your voltage source, which is 10 volt. Similarly, if I want to get voltage across R1, so how does the formula go now? It will be equivalent to V1 will be equivalent to R1 over R1 plus R2, and then multiply with my E over here. So very simple. Any voltage that you want to get across the resistor, that will be the resistor at your top part or your numerator part. Denominator part, basically the summation of all the resistors available. In this case, only two. If you have 3 or 4 or 5 or more than that, you just add all up over here. Okay, so that's what voltage divider rule is about. Okay, so this is just indicating the total voltage source. If everything is stacked in series, you basically just sum all up. Alright, to know that resistors is in parallel, you see a difference, right, between the one just now. If in series, it basically means that one end is actually being connected to the beginning end of the other circuit, the other resistor, I mean. So if you have it in parallel, alright, you see it's called in parallel connection when they have two nodes in common. Alright, let me teach you what a node is. Alright, node is basically something like this here. Alright, this is what we call it as node. If this is node A, alright, I also call this as node A, provided that there is no any other element that, or any element basically means like resistors or anything that is separating between the two nodes. Alright, so usually we call something in parallel, the resistor being in parallel, when they actually share the common nodes. Like in this case, here and here is the same node, here and here is the same node. Why we call it the same node? As long as there is no any other resistors or capacitor or inductor that separate them in between, this is considered the same node all the way. Alright, this is also the same node all the way. Okay, so they share the same node. Alright, and it's pretty obvious for parallel because you can see that it's like something hanging around and all that, right? Something's dangling and all that. So that's how we look at parallel. Okay, and how you get the parallel? Basically 1 over RT will be equivalent to 1 over R1 plus 1 over R2 plus 1 over and so on, so on. Alright, so in this case over here, it will be 1 over RA plus 1 over RB plus 1 over RC plus 1 over RD plus 1 over RE. Alright, sometimes and then that would be the 1 over RT, right? After you have got your answers and all that, what you have to do is just you inverse it again by taking it on 1 over the answer as well, because 1 over RT is equivalent to, this is what the answer is, right? So 1 over RT, after you have computed this is actually your 1 over RT. So your total resistor is actually your RT itself, which means you have to invert it again. Alright, do your maths. Basically it's just math stuff. I just want to stress though, sometimes it might not seem as boxy as it might be. It can be in terms of rectangular shape and all that. But as long as you know that they share a common node, like in this case, this is a node over here, but all of them share the same part, right? Even for this one, over here, over here, over here, you can see that there is no any other element that is separating them in between. So if everyone is sharing the same node, node A and node B together, you see C lies in between A and B, B lies between A and B, and so is A. So we call this being in parallel. Alright. So this is another way for you to calculate things in parallel. You can multiply them first and then divide the sum of the two resistors. Same goes for it being in 3 resistors in parallel and all that. So this is a different method, up to you which one you want to use, but I always like to still use the 1 over RT because this is so much simpler. You just don't care how many resistors we have, just plus all up and get what it is. Alright. Another law that we know is Kirchhoff current law. Basically, it says that the sum of current going in is equivalent to sum of current going out. So, like I said, the node, right? This is like a common node. You just look at this. I1 is going inside, right? This going in. I2 is going out. I3 is going out. I4 is going out. I5 going in. So if you just want to separate everything going by Kirchhoff current law, it basically means your I1 and your I5, these are current going in, right? So I put I1 plus I5 together, equivalent to, and the rest would be the current going out. How I determine it? Basically, if current going in basically means the arrow is heading towards the node. If it's going out, it's going away from the node. Alright? So just take note on the direction of the arrow and you will be able to come up with this. Alright, current divider rule. That's another one thing for you to know. Alright, for current divider rule, basically it's like, okay, for IX, for example, alright, if you want to get your current, you will get the RT over your Rx. Okay, your Rx is this one, and then you multiply with your IT, which is the current, the total current that's going on here. Okay, that's just a little bit of things that we can know about and all that. So if you look at this, this is a combination of different series and parallel, right? So always look at it by the node. Okay, here's how you look at it. So you always, if this is your terminal, right, you always look at it from the far endmost. Okay, and in this case, you know that this node and this node, they share the same node, isn't it? So this and this is the same, this and this is the same. So it's fair for me to say that your R3 is parallel with my R5, right? So if you see this thingy over here, it actually means that it's also indicating that it's in parallel. So R3 is parallel with R5, so it's also common sense that I would say that R4 is parallel with my R6. Alright, so if I redraw the whole thing again, this is my R1 and then this is my R2. Alright, and then like for this part here, the new resistors that I have over here, this will be my R3 parallel with my R5. How I get the parallel form? Just go by the formula, yeah? And same goes for this one. Okay, this will be basically the R4 parallel with my R6. Alright, and after that, how do you get the equivalent resistor? So this becomes a series already. You plus them together, then you get it, and then you solve one by one. Okay, and then it will be in parallel with this R2. You get it, and then after that, finally you plus with this one. Do give it a try because the answer is over here. Alright, so that's on AC circuit. Okay, we have looked at the series, we have looked at the parallel.